Hello, and welcome back to Learning with Lee. In today's episode, we are going to take a look at what are known as structures. Structures are the very first form of a complex data type we are going to examine. Later on, we're going to examine classes. However, because structures are the more archaic and older version of these two types of complicated data types, we're going to start with them. And the major thing is that you might remember how I discussed primitive data types, or things such as ints, characters, and the different types such as that. A structure, in case I were to, let's just for now create a header file so as I can store a structure in it, and this happens to be a common thing for what you actually do with structures, is that you tend to declare them or tell what is within them within a header file. So we're just going to call this one here, and we're going to be doing what is known as a linked list. So we'll just call this linked list.hpp. And within here, the way in which you define a structure is you just use the struct keyword. And if I name this such as, and I'll just call it a link within a linked list. And the thing about a linked list, and there's a couple things that we actually have to do here. So before I get into what a linked list actually is, one of the first things that you'll notice with a struct like this is that it has a scope following it. And it needs to have that scope after it, and we're going to put different things inside of there. But that also requires you to put a semicolon at the end after it. So for this, I'm actually going to give it a namespace. And for this, we'll just go with linked list. And copy this section bottom here so that our link is within our linked list namespace. So what we then need to do happens to be we need to define what is within our link. So for now, we're just going to put in here an int, and we'll just call it item for now. And it can be really any integer in the future. And what we're doing right now with the structure is that, similar to how int tells your computer I need a certain amount of memory to store this data, a struct is basically doing the exact same thing that is, except rather than just having a single item, I could then have, if I wanted to, a second item within here, so as that this structure would have enough memory to hold two integers. I could even technically have an array of integers in here. Right now it's treating it as a pointer. However, you can also go, I want a specific number of items in here, rather than it just being a pointer. So if I do that, probably have to clean it first, yeah. Because it's not necessarily going to notice that difference, but then building it. And as you can see, it still allows us to do that, even though now we're specifying how many items this is. So this would actually have enough room for 21 integers in it by default. One of the key things about it, though, is that if we consider our whole things about how we're passing either by reference or by value, structures are passed by value. So if I have this array in here, it will actually copy that entire array into whatever I pass it into. So if in the future I were to modify this merge sort to take in these links and I had an array of 20 items in there, I would end up copying every single one of those links set of items in there, which ends up being pretty large, and we'll get into how you deal with using structures by reference and by pointers to structures in a little bit. So the other thing you can do is you can actually reference a structure from within itself. So in this case here, the thing about a linked list is that it's similar to an array of memory in that you have sort of item 1, item 2, and so on and so forth, except in a linked list, what it is that these aren't necessarily in a contiguous block of memory. They aren't in a set of memory that starts at one point, ends at one point, and basically there's nothing else in between those 2 points that happens to be used for anything else. Whereas in a linked list, each link in that list happens to have a block in memory, and then what you do is you go, I want a link pointer for the next item. And if I wanted to, I could make this a doubly linked list, so as I'm not only pointing to whatever is next in the list after me, so as opposed to dealing with item sub 0, item sub 1, I can then take this, put this down here, and then we have previous item. And that will allow us to be able to look back and forward at what each side of this has. And in general, in the future, just a bit of a heads up, structs are not going to be used very regularly by us. However, at the same time, there will be times when we do use them. So let's now modify merge sort to use a linked list. Well, I'm just going to, for now, flat out copy all of this merge sort, primarily the merge sort alternative, over into its own separate folder for the linked list stuff, and I'll rejoin you once I've done that. So I may have gone a bit overboard, and as a result, I'm probably going to end up splitting this discussion over at least 2 episodes, maybe even 3 episodes. Initially, I had planned to cover structures in just a single episode, but since I'm now also introducing linked lists, and I really want to make certain that we can understand why linked lists are used as a particular container in programming, I'm going to need a bit of additional time, as well as because I want to do this in a fairly reasonably accurate and correct way of doing this. And as such, there's quite a few different functions down here that I had to create before I could even get into things such as dealing with the sorting portion of it, and the changes that entailed. So, before we actually really begin on any of that, let's head on over to Paint, and I can begin discussing with you why we use a linked list in programming, as opposed to some of the other containers that are out there. So, let's consider that we happen to have this here as our set of memory. And within here, we might have some blocks that are already in use, and these, just fill them in some. There. Say that we have another block over here in use, and then we decide we want to malloc and create an array. Because this is one of the reasons why we use linked lists, and that's that, let's say that I need an array that happens to be around this much space in memory, however much that would be. Well, it obviously can't use this free memory here and be continuous. This is even a smaller space, and then we have this one down here which might be large enough to fit it, but at the same time it's a matter of, in some cases it might not be. And as a result, without having the ability to split up this list into multiple segments, we might not be able to actually allocate enough memory for us to be able to store that. And as a result, there can be certain times in which, if you're dealing with really, really large data structures and the like, and depending on whether or not you happen to have a lot of free space in memory or not, you might have to split up your set rather than having it be a contiguous array of memory. Furthermore, in case we pop on back here and head on over to here, you'll see how in this other one, I had to know the size of my arrays when I initially created them. And we'll get into other data structures in the future that allow you to dynamically resize and the like, but the first one we're seeing here is this one here, which is a linked list. And that's because, basically with a linked list, if I just get rid of those, what I can do is I can go, okay, I'm going to have a section here, I might then have another section here, and then I can create one over here. And it just will be like, this guy links to that guy links to that guy, this guy links back around to the beginning if we aren't in a doubly linked list or whatever. And then it allows me to be more conservative with the amount of free space I have, because realistically what I'll do is it'll just pack this section over here as much as it can with a whole bunch of them. Go, there's not enough room there, and they'll start just moving some over here, and then we can have this nice little list going along here, and it's a decent use of our memory. And the other thing about it is that because, in case we do this on the heap, I can just go, I currently have, this is my current list, and just let's malloc another thing over here, another link in our list, and add it onto the back of the list. It's a bit more complicated when I then have to also not only change this one to point to here, but then also change this guy to point back to the original. but both of those happen to be fine options for what we can do. So that's one of the many reasons why we look at using a linked list. Another one happens to be that for what we were looking at earlier with how we had to sort it in case, let's say that I wanted to, well, let's just use this what we already have up here. And let's say that I had this element here, and right now our current list is just going across like this. And I want to take this element here, and I want to move it over into this position effectively in the list, so it's the second element in the list. All I have to do is I don't have to move all of these physically in memory like I would have to if I were dealing with an array. All I have to do is go, okay, rather than having all of that there, what I can then do is I can just go this guy down to here, then back to here, and then back through our list like this, and then this one becomes the last element in the list. It just is a matter of changing around the order that the things are linked in. And it's literally as simple as assigning a couple of pointers. And we're going to take a look exactly at how we do this in a few seconds, but for now, that's that portion of it. So the major question then is what does this change about our earlier merge sort algorithm? And just as a reminder, merge sorting is when we take our list, first split it down into a whole bunch of different sub-lists, and then go, okay, I'm going to take this element, move it into its correct position, move this guy into its correct position, so as that I don't have to reorder everything in the list. Well, the first thing is that we can effectively end up using, well, eventually we'll have the ability to only use the stack without ever having to use the heap. That's one option. The second thing is that, and currently I don't have it implemented that way just because I wanted to show you how I would make those changes, so as you can see both how it would be using the heap as well as how using the stack, as well as also to reinforce the difference in the cost of performance of those two. However, then beyond that, it's a matter of, for splitting it up, the thing with the list is that we could just go, okay, I have effectively a pointer here and a pointer here, and I can mathematically figure out what those pointers are. So as I have my A list and my B list, then I can split those into two separate lists effectively just by saying that this one here now has a length of 4 and this one now has that length on it. And you can, to a certain extent, do similar things with a linked list like this. However, the thing with a linked list is that it might end up being something like, I start out over here, I jump all the way over here, jump over here, jump back over here, jump over here, and it can be really messy. So I can't mathematically, in constant time, figure out where, say, the fourth element in that list is. What I have to do is I have to go, okay, let's go to element 0, follow its link to element 1, follow its link to element 2, and so on and so forth until I hit the fourth element. And as a result, it takes time to iterate over those, and you can't just go immediately to your fourth element like you can with an array. So that's a performance consideration you need to take into consideration when you decide whether or not to use a linked list. And we'll get more into that when we get more into data structures and algorithms in the future. But for now, it's a good thing to just start considering as a potential problem, because it will be a problem when we start dealing with advanced algorithms, as well as trying to make things more efficient. So we really don't have too much more time for today, so I'm going to thank you very much for watching. I hope you have a wonderful day. Take some time in order to really consider how linked lists in general work based upon what I've shown of these two structs. If you want to consider the sort of things you would put in a struct if you were to describe a student or a classroom, or in case you're more mathematically inclined, different types of vectors and matrices. Because all of those are things we're going to be dealing with in the future, and it just would be a good idea to start sort of planning that out now. Once again, thank you. Have a wonderful day.